Okay, hello guys. I'm going to resume where the from last week lecture, which my internet got problem. So basically, since all of the substituents may affect the benzene ring through either inductive or also resonance effect, we're going to see some examples on how these substituents behave in terms of their what you call the intermediate structures. Okay, so for example, this methyl group or alkyl group, it is an auto-para directing activators, meaning that if you have another reaction for this particular compound over here, for example, here it undergoes another nitration reaction, the new NO2 or substituents will be either at position ortho, which is 1, 2, or it could be in para position, which is 1, 4. So why it doesn't choose the meta position? As you can see over here, the percentage or the products form 63% of it is ortho, and another third of the products form is in para position. Okay, for meta, it is 3% or even less than that. Okay, or sometimes the product may not even form at all. So the reason, as you can see over here, all of the structures, whether it goes into auto, meta, or para, it form 3 resonance form. Okay, the more resonance structures, the higher stability it is for the intermediate. But then again, when you look at where the position of the C plus or the carbocation ion or the carbon positive ion is, you look at these two ortho and para position. As we know that tertiary carbocation ion will be the most stable form. Okay, hence in ortho and para position, there is a tertiary carbocation ion over here. You see, this is carbon. It is bonded to 1, 2, 3 other carbon. Same as well for this carbon. It is bonded to 1, 2, 3. Whereas in meta position, the highest carbocation ion it has is secondary, which is this one, secondary, secondary, and secondary. Same as well for the other structures that is available also in auto and para position. So that's why for alkyl groups, if you have alkyl groups bonded to the benzene ring, it will direct the new substituents either to auto or para position due to the most stable carbocation ion or the areninium ion form. Okay. Then we see example for hydroxy and amino group. So for this one, none product form at all for meta position, only ortho and para. So each of them have half percentage of product form. Okay, for ortho and para, they have 4 resonant structures. Okay, 4 resonant structures, unlike in meta, only 3. And then as you look over here, even though that all of the carbocation ion, this 1, 2, 3, this one also are secondary. Okay, this one also secondary, but these two are the most stable. Why? The reason is because the positive charge is no longer inside the ring. It is no longer at the carbon. So that is the most preferred position, and it will make the ring more stable because the ring is not, it doesn't have any charges at all. So it will make it more stable, and the positive charge ion is at oxygen. So this is the most stable form. Okay, unlike here, the structure is basically the same. Okay, all of the carbon positive charge or the carbocation ion is secondary only. Okay. Then for this one is deactivators for halogen. So halogen also direct the new substituents to either ortho or para as well, but then again it deactivates the ring. Okay, it make it less reactive. Okay, so from here you see this is chlorine. Say chlorine is more electronegative compared to carbon. That's why it is deactivating. It pull the electrons from the ring towards itself. So that is why it is deactivating. So as you look over here as well, ortho and para still have four what do you call the resonance structures. Meta only three, and then the most stable structures are in either ortho or para position. Why? Because the positive charge is no longer inside the benzene ring. Okay, no longer inside the benzene ring. It is already on the chlorine. Okay, chlorine. So that's why it is the most stable intermediate form. So hence ortho and para position are preferred. Then we go to the meta directing deactivators. Okay, the last one. Okay, this one, example like substituents is aldehyde, carboxylic acid, esters, amide. Okay, so this group it will make the ring less active. Okay, it pulls electron away as well from the ring. But then the new substituents that will be substitute one of the hydrogen in the benzene will prefer to go to the meta position. Okay, the reason is not because in the meta position, okay, it has the most stable carbon ion or intermediate structures. Is due to the reason that in ortho and para position, the least stable form of intermediate is formed. Okay, so it's like saying that the meta position win not because that it has the most stable intermediate. It because in ortho and para it has the least stable. Okay, it's like it's winning not because the meta position itself is good. It's because the others are even worse than these three intermediate. Okay, if you look here, the intermediate is exactly the same as this one. Okay, auto para directing the activators and also auto para directing activators, meaning that in meta position the intermediate is we can say constant. Okay, the difference is either in auto or para position. Okay, but for this meta directing the activators, it prefers to go to meta position due to the reason that in ortho and para it has the least stable form of intermediate. Okay, not because here it contains the most stable form. Okay, this is the summary table for effect of substituents and in aromatic substitution. Okay, this slide is to me is one of the most important part of this module or the this unit or chapter. Okay, so maybe you can print and paste on your study table, okay, and try to memorize, especially this what do you call this arrow over here with all of the different substituents. Okay, here it is already notified what is meta directing activators, example of group, and also ortho para deactivators, halogen, ortho para directing activators. So or you can also refer to this table. Okay, you have alkyl group, you have hydroxy and amino, your halogen, and all of this deactivating. Okay, if you look over here, amino group is the most activating group for the benzene ring itself, and it is an ortho para activators. While here, ammonium ion, okay, and with R3, okay, not NH4, and R3, it is the least reactive. Okay, it will make the ring or benzene ring very, very, very non-reactive. Okay, so if you have a reaction with this as a substituent, then the reaction probably gonna go very, very, very slow. Okay, why do you need to know all of this? Okay, here is the benzene, normal benzene ring with no other substituents. So why? Okay, due to this reason. So here we see that trisubstituted benzene, additivity of effects. So let's say the original structures that you want to have another substitution reaction already contain two different substituents. Okay, the rest previously all of it contain only one, or in fact just normal benzene ring. If the benzene ring doesn't have any substituents, you can put the new substituents anywhere, here, because where you put the substituents will be regarded as carbon number one. But if you have one substituents, then you just follow whether it is auto, para, or meta. But then now if you have two different substituents together, so which direction that you want to replace or substitute the new substituents? Okay, here it said that if the directing effects of the two groups are the same, then the result is additive. So what does it mean here? Let's take a look. Here we have alkyl group and also nitro. So if you look at this scale again, so that's why I said this is very important. This is alkyl group. It is an ortho-para directing activators. And another one is nitro. Nitro is meta-directing. So if you go back here, so this is CH3. Ortho-para will be at this and this position. So it can be here or here and also this position. So the para position is not a free, meaning that it's not available because there's already a nitro group over here. So you can either put here or here. Okay, now for nitro group, this nitro group, from the scale, it is a meta-directing deactivators. So meta-directing meaning that it will be meta-directing from the perspective of nitro. Okay, so this is nitro, meta will be at this position or this position. So meaning that both of these points towards the same direction. So you can either put here or here. So you end up with this product. But if the directing effects of two groups oppose each other, meaning that one is pointing towards this carbon while the other is this carbon, the more powerful activating group decides the principal outcome. Example, if you have OH and CH3. So this is OH and this is CH3. Both are ortho-para directing activators. So if you go back here, so for OH, ortho, para is not available. And also for alkyl group, ortho, and para also not available. But as you look over here, there are 4 different positions in which you can put the new substituents. In this case, it is a nitro group. So from here, you have to compare between OH and the CH3, which one has highest reactivity. So in this case, it is the hydroxy group or the OH group. So you follow the OH director. Okay, so meaning you can either put over here or here, ortho. So hence you get this structure as your product. Okay, you don't follow CH3. Then for meta-di-substituted compounds, so if you have something like this as a starting material and then you want to chlorinate it, so this CH3 from the scale, it is an orthopara. This is chlorine, halogen. So all halogen is what? From the scale, it is an orthopara deactivators as well. So orthopara, orthopara. This one also ortho, para. So all positions are freely available. It points towards, this is additive effect. Okay, both pointing towards the same direction. But at this carbon, the new substituents cannot come in because it is too hindered, or we say that it has steric hindrance. Okay, because this is on paper, you just see this as CH3, but in reality, if you draw using a 3D structures, this carbon contain 3 other hydrogen. So it's quite bulky over here. The new chlorine ion is also quite big, because the ion size itself is quite large. So it is hard to go in and attach or bond to form a bond with this carbon. So it prefers to go here or here. So you end up with these two product, either one of this product, but not this one. If you still want to have adjacent substituents like this, okay, it is best to start with an ortho substituted compound, meaning you have to start with side by side substituents, then you can add the new one here or here. All right. So synthesis of tri-substituted benzene. So all of the knowledge or information that you obtain from the beginning of the lecture until this slide, what is the function of it is, the use of it is to in terms of synthesis. So synthesis what? Some of the drugs that we have seen example earlier in the first few slide of the unit. There are some examples of drug, okay, which is benzene derivative. So all of these drugs need to be synthesized. So how are they being synthesized is based on where to replace the substituents. So for example, here, if you want to obtain this product from benzene, so you have to develop a synthesis pathway. Synthesis pathway is something like this, where you just draw your starting material, what reagent that you need to use, what is the reaction condition, and the products that you will get. So that is what you call as a reaction pathway. Okay, so probably in your exam there is a question coming out uh, from benzene, develop a synthesis or reaction pathway for this product. So what you need to do, you know that this is bromination, this is nitration, this is Friedel-Crafts alkylation, or you can also Friedel-Crafts acylation. There are only 5 types of reactions. Okay, but which one of this reaction is going to be placed first or second and third? So all of this is determined by this scale over here. Okay, you have to check the reactivity and you have to check the directors, whether it goes into meta or orthopara. Okay, and they might be more than one way in which that you can obtain the compound over here. For example, here in benzene, you can either have a Friedel-Crafts alkylation first, or you can have bromination first. So you can have this alkyl or bromine, and then proceed by bromination for this one and Friedel-Crafts alkylation for the one below. Because this is orthopara directors, and this one is orthopara directors. So you can put the bromine at para position. You can put for this the alkyl group at para position. Then the last one will be nitration. So for nitration, between bromine and alkyl group, the CH3 methyl group have higher reactivity. So it will follow this one. So it has ortho, and para. Para is not freely available. So you can put your NO2 at ortho position. Okay. Then here, you look at over here. You cannot have bromine and nitro group first. Then the last step, you want to add the alkyl group, because the deactivated ring will not undergo a Friedel-Crafts reaction. Okay, remember, Friedel-Crafts, you have the limitation. So if it contain any what do you call this, deactivating group, okay, the reaction will not proceed because it is very hard to form carbocation ion. Okay, so take all of those into account so that you can synthesize this product. Okay, then another example, here we have chlorine, sulfonic acid, and also just an alkyl group. here you have this, it undergoes acylation, Friedel-Crafts acylation, okay, with an acyl group. So this is acyl group, this is acid chloride, this is acyl group. Then from this acyl group, it straight away form, this is basically a ketone, straight away undergoes chlorination. Then after chlorination, it undergoes reduction reaction to turn this carbonyl group into CH2, normal alkane. Then the last step will be adding the sulfonic acid. So why from this propiophenol, it doesn't straight goes to the reduction first, then only add chlorine. So this is the way you uh, uh, you want to put where the substituent is, because if you convert it into an alkene first or alkyl group, this will be a orthopara directus, whereas you want to put the chlorine in meta position. So what you call the carbonyl group or aldehyde or ketone is a meta directus. Okay, so you have to plan ahead where you want to put which reaction you want to have first. Okay, so over here, as you look, there's only one way in which the product can be obtained. So it depends on the substituents over here and reaction pathway that you use. Okay, so these are sort of like summary of all of the reaction. There are 5. Okay, alkylation, another one acylation, the curve acylation with different reagents. Okay, and this is also the same. Common substituent groups and their effects. Okay, orthopara directus. Okay, but I believe this is the most useful slide in this unit. Okay,